advanced study in Seoul here with us. And for those of you who are not working in physics, Professor Kimyeong Lee did his PhD at Columbia University in 1987 with Professor Eric Weinberg. And then he had various positions, including visiting fellowship at the Institute for Advanced Study in Princeton, and various faculty positions at Columbia University at Boston. And then he became, a few years ago, the vice president at KIAS. Since 1999, he is a professor at KIAS in the School of Physics, working on various aspects of supersymmetric gauge theories, quantum field theory, and string and M theory. Most notoriously, recently he has been working on various aspects of higher dimensional supersymmetric field theories in five dimensions mainly. And related to his recent work, today he is going to talk to us about symmetry, the monster, and conformal field theory. It's a pleasure to welcome you here, Professor Lee.
Thank you. So first of all, I'd like to thank the Professor Rak-Kyeong Seong, who just studied in School for Mathematical Science at UNIST. And this is also my first talk toward the mathematicians, even though I have some math background in undergraduate, but I strayed away to physics. But there are a lot of good, interesting things happening in math, and one of these the classification of the finite groups and the monster. And I was looking forward to do something about it. And last few years, we are lucky to get into the subject and make some contributions. So let me enlist my collaborators. Dr. Jin Bae is currently in Oxford University as a postdoc fellow, and Professor Seong Lee is a faculty member at KIAS, and Brandon Ray Hong is still PhD student at Stanford, I think, and Professor Jeffrey Harvey is in University of Chicago, and Matthew Sakis is a postdoc fellow in KIAS. He got his PhD from France, and he's moving towards to quantum chemistry and also AI. And Dr. Ji Hao Duan is also a postdoc at KIAS. And references, I would like to say, because I'm a physicist and I want to enlist some references besides my work. And there's Frankel, Lepowski, Brilliant, on vortex operator algebras and monster, and then Grace on my life and times with sporadic simple groups, and so on. And the last one is the Ronan, who wrote a popular book on symmetry and the monster, which partially overlaps with my title. So outline of the talk is first I'll talk about symmetry. And symmetry means transformation and invariance on the transformation. And then I'll talk about quantum field theory in simplest way so that some mathematicians here can pick up something useful out of it. And then I'll review very briefly sporadic groups and the monster group and also monster moonshine. And then I'll again coming back to physics, conformal field theories. And then I'll show how one can break moonshine module or monster CFTs into smaller bits. So symmetry is something seen is together and metric is measure. So you are measuring two things together and comparing two things. And the Korean word 대칭성 is exactly like that. You confront two things, and the 칭 means scale. So you are measuring two things against each other. Now, if you look at the symmetry, okay, so here's the title is poem by William Blake, 1794. And I had a very nice picture of the tiger, which is gone. Tiger, probably use a lot of pictures of tiger, but you never noticed their face is symmetric like us on the left and right. Their marks, black and yellow spots are symmetric, more or less. So that's why Blake wrote this beautiful poem. Let me just read the first paragraph. Tiger, tiger, burning bright in the forest of the night. What immortal hand or eye could frame thy fearful symmetry? So this captures what we want to do exactly here, or what people have been doing. So symmetries are in the forest of darkness. People are discovering new symmetries. And you are trying to imagine how this symmetry is inside our general look of the world. I'm sorry that I don't have the tiger, picture of the tiger. Oh, again, pictures are gone. I don't have many pictures. I just have it. So very simple. So G2 symmetry is simplest possible symmetry, which is either reflection or 180-degree rotations. And reflection, I got the butterfly I saw a few weeks ago, which is alpine black swallowtail butterfly. It's a big bluish, greenish, black butterfly, which is around in Korea, Japan, and also China. It's beautiful butterfly. I haven't seen it before, but it has very, very nice reflection symmetries. On the other end, the 180-degree rotation, I was copying this beautiful design by, I guess, some novel, Angels and Demons. I don't know, maybe it's too old book. It has a very nice design, which is invariant on the 180-degree rotations. So those are simplest possible symmetry one can see. Oh, right. So that's that, pictures. Now, one can imagine such a discrete symmetries, but instead we can think about continuous symmetry, like two-dimensional rotations and three-dimensional rotations, which we have studied in first in calculus or first in physics course. And two-dimensional rotation is related to abelian Yuan transformations, and three-dimensional rotation is this special orthogonal group SO3. So it's very simple symmetry we can see everywhere in the world. So generalization of this continuous symmetry, like rotations or three-dimensional rotation, is called Lie groups. And the symmetry transformation is captured in mathematics as a group. So what is the group? Okay. So what is the group? So symmetry means symmetric transformation, and they form a group in mathematics. And the group is a set of elements with a binary operation, which is group multiplication. And so any two elements, when I multiply them together, again, it becomes a group element. And it satisfies associativity and also identity, unique identity, such that when you product with a group element, it's itself, it's invariant. And then there is a unique inverse for any group element. Very simple mathematical structure. And this group is basically capturing the symmetry of the things we see. Now, I talked about spatial rotation, especially in space. And we know very well that when we rotate by 2 pi, we are coming back to our starting point. But nature is clever than that. Turns out there is something called the special unitary group, SU2, which has, as a Lie group, has a manifold of the 3 spheres. And also SU2, which is 2 by 2 matrix with complex entries, whose determinant is equal to 1, and GG dagger is equal to 1, special unitary group, is a double covering of SO3, spatial rotations. And difference between them is that in SU2, you can have a two-dimensional representation, two-dimensional vector space where SU2 matrix is acting on it, and they are called the spinors and spin up and down. And this SU2, which knows the difference between 2 pi and 4 pi rotations, because on the 2 pi rotation, it changes by -1, it changes sign, and such a things appears in nature as electron spins. And people have been using these spinors to study qubits, quantum mechanics, quantum computers. This is one of the hardest topics in current science. So very simple, presence of spinor just pops in by studying how things transform on the spatial rotations. And amazingly also, because of this fine distinction, particles in the nature get split into two kinds of particles. If you have half integer spins like spinors, and then they are called the fermions, which is the difference between 2 pi and 4 pi rotations. And if you have integer spins, then they are insensitive to 4 pi rotations, and they are called the bosons. So understanding symmetry of nature will teach us so much about it. And also, what kind of symmetries are possible is the subject of this talk. That monster group is one of the most special kind of symmetry one can have. So these continuous symmetries, like rotations, and especially compact Lie groups are classified maybe 100 years ago, and they are into this 9 classes. There are A, B, C, D type, which is SUN, SO2n plus 1, and SP, special symplectic groups, and SO2R groups. They are classical Lie groups, and then there are exceptional ones, which is E6, E7, E8, and F4, and G2. And especially E8 group is a 248-dimensional adjoint representation, which is the smallest representation of the group. And so we'll talk about E8 groups later on. Now, so that's the symmetry and the group. Now, on the other hand, there is a nature, and there is a theory, which is framework, which describes the nature, which is called the quantum field theory. And what is quantum field theory? Again. So periodic table of atoms were discovered in 19th century. And we know all the matters in the nature is made of the hydrogen atoms, helium atoms, and all that. And each atoms in 20th century found to be made of the nucleus and the electrons. And nucleus is again made of the protons and quarks, and protons and neutrons, and they are bounded by very strong interactions. And then people studied and found that protons and neutrons are made of the quarks, up quarks and down quarks of fractional electric charge. So at the end, even though matters we see is coming in all kinds of shapes and all kinds of properties, but they are made of the very simple objects, which is called leptons and quarks. And the number of particles, there are lots of them, and they are called the identical particles. So for example, all the electrons in this universe are identical. They have the same electric charge and same spin up and down. That's all they have. There's no distinction between them. And you cannot put a tag on the name, you cannot put a name tag. If I put two electrons together, then because they are identical particles, you cannot distinguish them. And these identical particles are made of the, as I say, fermions and bosons. And fermions, especially of spin 1/2, constitute the matters of nature, and bosons of spin 0 and 1 generate the forces like strong interactions, weak interactions, and Higgs interactions. So quantum field theory arises as a combination of classical field theory, like electromagnetic field, and special relativity of Einstein, and quantum mechanics. And when you quantize the theory, so when you transport this classical field theory to quantum field theories, the quantas are appearing becomes particle, identical particles. So as I said, all the electrons are identical, and there's only one kind of field, spinor field or Dirac field, who, when you quantize it, it generates electrons. And this quantum field theory is a framework for standard model of elementary particles. Right. So, for example, if I look at the elementary particles, as I say, they are split into fermions and bosons. And fermions are made of leptons and quarks. And leptons are, for example, electron, muon, tau leptons and neutrinos. And quarks are up, down, and so on. And so protons and neutrons are made of these quarks. And then there are interactions bounding them together. For example, these strongly interacting quarks are bounded by bosons. And there's a photon, which is interacting with all the electrically charged particles. So for example, we see photon every day, every moment. Our eyes can detect visible photon. I hear the minimum number of photons we have to, which can trigger our eyes are 6 or 5. Single photon will not trigger our nerve cells, but if we 6 visible light photon cells hit our eyes, then it will trigger our brain signals and send the signal to our brains. And Higgs bosons, which generate the mass of the particles of the leptons and quarks, and the weak bosons, again, which is weak interactions. And here is this famous curve, which captures the theory of the standard model in terms of Lagrangian. But unfortunately, again, the image is gone. There's a Yang-Mills term, Dirac term, Higgs term, and that's it. And this is very simple Lagrangian captures the theory of all the elementary particles. And this standard model captures pretty much everything we see, besides black gravitational force and also some interaction supposed to be there for dark matters and dark energies. Besides that, it captures pretty much all the physical world we see. And this theory, again, is written in very beautiful way in terms of SU3 cross SU2 cross U1 gauge symmetry. And the whole page is gone. I'm sorry that I should have prepared. No, not whole page, but whole picture is gone. But it will be less important later on. So, right. So quantum field theory is a very interesting physical theory and some tool which physicists have been using for last 100 years extremely fruitfully. And it has been extremely powerful in describing particle physics and also quite important part of condensed matter theories. So when we describe some collective behavior of physical world, quantum field theory can be a quite powerful tool. And also, quantum field theory extended itself beyond its own device by ADS-CFT correspondence. So quantum field theory turns out to know about quantum gravity and also black holes and string theory, which is amazing. This is very way beyond the original intention of string theory. String theory was standing independently from quantum field theory, but now they are in the same mathematical tool or landscape, and one can go back and forth. And also, quantum field theory is a new kind of mathematics, which is not rigorously defined unless in very specific case, like certain kind of topological quantum field theory, or recently Liouville quantum field theory in 2D. Besides those theories, this general quantum field theory is not well defined as mathematical theories. And it's motivated by physics, and it has many, many applications in mathematics and physics. It's like original calculus of the Newtonian Leibniz, which was invented to understand the math and physics, but has become extremely powerful in mathematics and also physics, but only defined hundreds of years later, when mathematicians can define calculus rigorously. And quantum field theory is somewhat in a similar situation. And also, some people call this is a physical mathematics because quantum field theory and also its stringy version of it has enormous implication in number theory, geometry, representation theory, geometry, Langlands program, and so on. So those fields, some people call physical mathematics. And some mathematician called quantum field theory as calculus 5. So calculus means small pebbles. So it was a device to count things. So that's calculus 1. And calculus 2 is Newton and Leibniz, infinitesimal differentiation and integration. And multidimensional calculus, including complex analysis, is calculus 3. Now, calculus of variation, which is infinite number of the differentiation of infinite number of variables, is calculus 4. Now, calculus 5, if we think about Feynman path integral, then that's one way of defining quantum field theory. So it's infinite dimensional integration. And when you do integrate of infinite dimensional space, usually things goes wrong, and it's very hard to define things well. And quantum field theory is exactly at that place. So physicists, even though we are not mathematicians, we are playing the kind of fire. When you are playing with fire, you have to play with really carefully, otherwise you will get burned. But if you treat it right, you get something quite productive. And that's what we've been doing that for the last 100 years, being quite productive. Now, let's look at the simplest quantum field theory, which is scalar field. So we are divided, as I said, quantum field theory is the amalgam of the special relativity with classical field theory. So we choose space-time to be two-dimensional, and the space direction is x1, and the time direction is speed of light times time with x0, and the space-time metric is given in this Lorentzian form, -1 and 1. And the scalar field is like an amplitude of sound or temperature. Is defined at every space-time point, and their dynamics is determined in terms of this action with integration of Lagrangian density, and from which one can read the field equation, which is very simple wave equation, hyperbolic equation, which is a linear equation, so one can solve it trivially, and then it's a linear superposition of the right moving wave and left moving wave. Both of them are moving with speed of light. Now, suppose your space is compact, then instead of going to wave moving to a spatial infinity, it goes around. And then in that case, we can always make a Fourier transformation of the wave. And then right movers and left movers, so we can expand in Fourier series, which satisfy equation of motion. So they move with the speed of light on the right side and the left moving. And then we impose a reality condition, and then that gives us condition on the coefficient of Fourier series. And that's the very simple classical field theory on 2 dimensions. Now we can quantize the theory by putting a commutation relation between field and its momentum density, and this is a very relative generalization of the quantum mechanics, quantization, and that produces this commutation relation between coefficient of the Fourier coefficient, and that leads to the vacuum of the theory where all the annihilation operator on vacuum goes to 0, and then you create the particles of, say, momentum n moving moving along the right direction by applying this creation operator to the vacuum. So Hilbert space of the Fock space of particles, elementary particles, are now generated by quantizing the field, and each elementary particles are characterized by its momentum along the circle, which is discrete integer. And then if you create creation operator R times, then you are creating identical particle, R identical particle of momentum n moving to the right. Or you can produce particles moving to the left. And then you can also apply different momentums and so on. So that's how you produce identical particles out of quantum field theory. So it's very simple, straightforward, simple tool, because we are doing free particle field theory. Interacting theory is very difficult, mathematical, but free theory should be very easy. Now, for these theories, especially we can think about partition function of the right movers or chiral state created only by creation operator moving to the with am plus, which is basically you are looking at the Fock space of the particles moving with speed of light along the say time-like directions. Now this partition function turns out to be a trace of q some weight times h plus energy and momentum. They are identical because it's massless particles divided by 2. And this one, partition function, which is just counting for each number of Fock spaces, the weight q, is given in this simple form. And this form is just inverse of the Dedekind eta function. And of course, Dedekind eta function was invented way before quantum field theory, but Dedekind eta function, inverse of the Dedekind eta function is partition function of a chiral scalar boson on a circle. And especially if you look at just one term in this Dedekind eta functions, inverse of it, then 1 over 1 minus qn is 1 plus qn squared plus and so on. And this contribution from momentum and single particle state to 2 particle state, 3 particle state, and so on. And if you don't take the inverse, then Dedekind eta function itself is the partition function of, even though I don't have time to explain this, let me just say that for the chiral Majorana spinor. So I said particles are made of bosons and fermions. If I imagine the fermion moving with speed of light along the say right direction, its partition function weighted is -1 to the fermion number is Dedekind eta function. So having a Dedekind eta function, one can see right away you can relate that to bosons and fermions. So math and physics, even though they look so far away from each other, they are just standing next to each other. Now, in Dedekind eta function, there is a q to the -1 over 24. And you wonder, what's the origin of this? Of course, physics can explain this one too. So that comes from vacuum energy of the theory, which comes from each harmonic oscillator. If you learn the quantization of harmonic oscillator, then there is 1/2 times omega, which is h bar omega, which is the vacuum energy of harmonic oscillators. But we have a harmonic oscillator. Each particle is created by a harmonic oscillator corresponding to the wave moving with speed of light and of frequency 1, 2, 3, 4, and so on. So that's the total vacuum energy. And if you do regularize this vacuum energy, which is obviously nonsense, using Riemann zeta functions, and then that's -1 over 24. Okay. So vacuum energy is this q to the -1 over 24, which looks very strange from math perspective in some sense, even though it has nice modular properties and so on. But physics captures it right away, is the regularized vacuum energy of these chiral scalar bosons. And so if I think of it, this is just single scalar field, which describes oscillations, but sometimes we can have scalar field itself is periodic. In that case, one can have winding modus, and then constant part of the wave can have a non-trivial space dependence. So as you go around the space, this scalar field have n windings. And the theory, when radius of this compactification is square root of 2 times k, is called the U1K Witten model, about which I'll tell you more later on. And string theory is a generalization of quantum field theory as some string moving in, say, some space-time dimension, and the string itself is vibrating. So it's a generalization of what we just did. And again, it has an implication in string quantization. And again, you may have heard of the bosonic string theory is constant in 26 dimensions. And at the end, if you look at it, it's 24 times 2 is 26. And 24 is basically you have a 4-dimensional space transfers to this string moving with speed of light. And then you have vacuum energy coming from the left mover is -1 because it's -1/24 for each chiral spinor mode scalar field. And if you have 24 of them, it's -1. And so left mover, right mover has -1, together -2. Then this spin 2 object has mass 0 because it has energy 2 against the vacuum. So they become graviton. And graviton is basically the source of the all gravitational interactions. And the string theory captures the quantum gravity because of these simple observations. I will not say much about string theory here. Now, so as we just talked about theory where scalar fields compactified on a circle, but we can generate higher dimensions. For example, oh yeah, there's one more picture. SU3 root lattice is made of those two simple roots of SU3. Then you can generate the integer coefficient. Then you can generate lots of dots, and then you can imagine space, two-dimensional space modded out by this root lattice. Then it's some sort of torus, and then one can think about scalar field living on it. Similarly, higher dimensional lattice of the distinct point. If it is positive, if inner product is positive definite, and integral if inner product is integer, and even if the length of the each lattice point is even, and the unimodular if the dual lattice is identical to original lattice, and it is a lot of constraint, and with this kind of constraint, they give a very special kind of lattice, and it can exist only when dimension of space is 8 times integer, and 8 dimension E8 root lattice is unique, even unimodular lattice. And especially E8 root lattice has length 2, square length 2 lattice point, 280 of them, 240 of them. And then there are 8 points in origin, so together 248 dimensional representation is shown. Now, Leech lattice was lattice in 4-dimensional space. Before that, let's think about 16-dimensional space. Then there are two kinds of even unimodular lattice, which is E8 cross E8, or spin 32 divided by G2. And those two lattices are related to heterodic string theory. Now, 24 dimensions, there are 24 positive definite even unimodular lattice, which they are called the Niemeyer lattices, and which was discovered in 1973, about 50 years ago. I guess most of young people, it's so long time ago. For me, that's the time when I was in high school. Now, Leech lattice is unique 24-dimensional positive definite even unimodular lattice without any root, which means root means square length is equal to 2. So all the Leech lattice minimum length square is 4. And such a lattice is unique. And John Leech in 1968 discovered it as part of finding the densest sphere packing. So when you have spheres, identical spheres, and you try to pack the sphere, some dimension is these spheres, and the center of spheres can make some lattice, and most dense lattice packing is in 24 dimension, and that's through the Leech lattice. So after Leech found this lattice, he was asking around what's the symmetry group of this Leech lattice. And John Coney was around, I guess I forgot to put the date. He found that there is a new kind of a group, Coney 0, which is twice simple group, Coney 1. That's the Coney discovered, and the Coney discovered 3 sporadic groups, Coney 0, Coney 1, Coney 2, Coney 3. And one can think about also string theory and Leech lattice, which is somewhat related to representation of the monster groups. Right, so that's quantum field theory. So we just imagine the lattice, and we imagine the scalar field living on some torus, which we get by modding out the space is lattice. Okay, so that's the kind of quantum fields we are imagining. So let's think about, again, the symmetry groups. So I said symmetry generate groups. And so let's look at the groups, especially this, not the Lie groups, which is continuous groups, but finite groups, which is discrete groups. And okay. So something is missing, but I don't know what is missing. Oh, okay. So now I see what is missing. So that's just a Wikipedia picture. I guess whenever the size of the file is big, this guy is rejecting. If we can do it, I guess, I think it'll take too long time. Yes, sorry, we should have checked it. Put the whole file on the web so that you can see the missing part of the story. So, right, so finite groups are made of the, let's see. Right, so sorry, the first thing I have to do is see whether my file, so all right, so this atlas of the finite groups captures the all the classification of the finite groups, and especially you just saw the picture of the John Conway who passed away recently because of COVID infection. Now, simple finite groups made of the infinite series and the 26 sporadic groups. And infinite series, obviously, cyclic group with prime GP, and then alternating group, which is even subgroup of the permutation group. And then there is groups of Lie type, Chevalier groups, Steinberg groups, and Suzuki groups, and Suzuki Rie groups. And Rie here is Professor Im Tak, who is a Korean Canadian who passed away some time ago. Now, 26 sporadic groups are made of 20 happy families and 6 paria groups. And if you look at the wiki, then there are this classification. So if you look at the red ones, then they are called the first generations, discovered by Matthew in 19th century. And second class is these green ones coming from the monster, Ricci lattice. Remember, Kone 1 is related to symmetry group of the Ricci lattice. And then there is the third generation related to monster groups. And then there are 6 paria subgroups, which is not related to monster directly. Now, monster group was discovered in 1973. In math, usually credit goes to somebody who proves, but monster group itself is an idea, and I think the name goes to Fisher and Grease. They did some important works along the way, but the idea, I think, counted there. That's how physicists give credits. And the monster group is the largest sporadic group, and smallest non-trivial representation is 1968-83. And then as a group theory, it has 2 kind of conjugation class, means that of involutions. So involution means the square of this group element itself become identity. And then congruence means if 2 elements are congruent, if they are related by transformation G, X, G inverse is equal to Y, then X and Y are congruent. And so using these congruence relations, one can divide the group element into congruous classes. And then there are 194 classes, and the number means the order of each element in class, and then A, B, C are different class of the congruence groups. Now, monster moonshine was discovered around 1977. So Klein J function has been known from 19th century, which is unique, which is invariant under SL2Z transformation, which is defined on Poincare upper half plane, and also is unique with a simple pole at the cusp at tau equal to I infinite or Q equal to 0, with residue 1 and the value of the J function at these 2 points is 0 and the 12th cube. And so J tau as a series of Q with a cubing exponential of the 2 pi I tau is given in this series. Now, what John McKay have observed, who is not really professional mathematician, he's more computer scientist working on mathematics like group theory, character tables, and so on. He observed that this number coming in Klein J function, which is identical to the minimal dimension of the monster group representation plus 1. And then he told the Thomson, and then they generalized to higher numbers, and then they found this very nice relation between monster group and the Klein J function. Klein J function is one of the most elementary objects in modular functions. And number theory is nothing to do with groups and representations. So it looks like so outreach, outlandish. And that's why I guess Kane and Norton named this relation as a monster moonshine. Moonshine means something outlandish, something unbelievable, something ridiculous, something like that. So this capital tau J, which is small j minus this constant number, is given in this form. And this Q square term later on we'll say related to energy momentum tensor of the conformal field series. And this is like an object which is similar to energy momentum tensor, and their algebra is called the Grease algebras, which can be again derived easily from the conformal field theory perspective. So moonshine module is that, so module is like a generalization of vector space. So remember spinor representation, we have two-dimensional vector on which SU2 is acting on. Similarly, module is like a big object on which this finite group is acting on. So it's a generalization. And this V natural is a module with a symmetry group is this Fisher-Grace monster group. And that has been shown by, expressed by Frankel, Lebowski, and Murian. The way they showed it is they start with again 24 chiral bosons. Instead of small fluctuation, now they are living on a torus. Scalar field itself is compact, living on torus, 24-dimensional torus. And this torus is defined by Ricci lattice. So you have a 24-dimensional space, and then you divide by Ricci lattice. Then you have a very discrete shape of the torus. And then from the field theory, right away you can see there are C equal 24 holomorphic quantum field theory, conformal field theory, with partition function given in terms of the theta function related to lattice, and then divided by eta to 24, which is exactly a perturbative contribution of the 24 chiral scalar field. And then they calculated that is J plus 24. So there's 24 additional bit because you have 24 scalar field. But this theory is invariant under this G2 symmetry, which is changing the coordinate XA to minus XA. And then there's very natural way of doing OV folding in field theory. And using that OV folding, and then you get the G2 invariant projection of twisted and untwisted sectors of the theories and combine them together, and then partition function turns out to be exactly J tau, which is what you want for representation of the monster groups. So that's how they found symmetry. So previously I said so I want to show that tiger has symmetry, right? So due to reflection symmetry. So we see the object, then we see the symmetry. But this is all the way around. They see the symmetry monster group, then they only see the object, which transforms into this monster group. That's the monster moonshine. And that turns out to be this Klein J function. Right, so this is all done. About 1988. So what can you do after that, right? Mathematician understood monster moonshine, and I think somebody got also field medal by putting everything in very precise terms and proving few things. Now, so, and then you wonder, what about the rest of 26 sporadic groups? Do we know the conformal field theory corresponding to that? Right, so monster group is at the top, so that we know from this leaflets. What about the rest of the guys? So that's the question one could ask. And unfortunately, there are some progress by people, and we want to be more specific about it. So along the way, John McKay again had a remarkable discovery. Not only moonshine, but again, people are looking at it, this conjugate class, especially 2A class, which is simplest involution. And then even though they are conjugate to each other, if I multiply 2 elements, then they don't need to be identity. Involution means when you multiply to yourself, it becomes identity, but not in the same conjugate class. And people have shown they belong to 1A, 2A, 3A, 4A, 5A, 6A, 4B, 2B, 3C conjugate class. If I multiply two of these 2 elements in 2A element. And John McKay said, oh, this number I saw before, and they are related to extended EA thinking diagrams. So if you look at the extended thinking diagrams, forget all the letters, group names, and this is basically the hallmark of the extended thinking diagram. This is the lowest simple root, and then rest of it is such that the wholes, when you sum all the root with different multiplicity is equal to 0. So it's a very famous number. And then you can see right away this 2 element is related to extended EA thinking diagram, which again looks ridiculous. I mean, monster modules, and they are nothing to do EA, but somehow 2A involution knows the EA symmetries. And these 2 elements of 2A generate a dihedral group DNX of a subgroup of the monster groups. And then, so some sense, you have gigantic monster group, and then you want to take out tiny bit of it and see what's left of. And then people found this monsteralizing pair, which means the pair of the groups is almost like a direct product. Such a way, monster group is direct product of this guy divided by something. And so, and they are committing each other completely. Okay, so you are dividing huge monster into 2 pieces. And if I look at the 1 element and then multiplying itself is trivial, so the remaining group is baby monster, and this guy is some Lie group type. This is Fisher 23, the second largest Fisher group, and the McLaren group, Harald and Norton groups, Fisher 22, and this Thomson group, and again Lie type, this Kone 2, second largest Kone group. So that's how people McKay observed that extended EA thinking diagram is related to monster and these involutions. Now, what we have done is we followed these trees, and we found all possible corresponding VOA or conformal field theory. So we found examples. This looks too busy, so let me look at the other one. So the tool we use is the conformal field theory, and conformal field theory is 2-dimensional theory, which is generalized not only Poincare symmetry, which is special relativity symmetry, plus dilatation, which is scale of the space-time, and then special conformal transformations. So for example, if I use Euclidean coordinate, then I have Euclidean R2 space, and this using complex coordinate, this standard conformal symmetry is made of the generate the SL2R symmetry, which is G goes to G prime, Möbius transformation, which is made of translation, dilatation, and inversion. And the conformal means the angle between two vectors is preserved under this transformation. And this has been generalized to Virasoro algebras, enlarged as a holomorphic transformation. So if I remember, that was a rational transformation of Z, and one can generalize it to arbitrary holomorphic transformation, especially infinitesimal transformation is generated by these operators. And if we insist this symmetry on quantum field theory, which means that quantum field theory doesn't have any scale because the dilatation changes the relevant parameter, mass parameter. So theory doesn't have any mass scale, no, there is no coupling constant scale, length scale, so it has to be conformal. And then once we do that in 2 dimension, it generalizes to series infinite dimensional representation, which is called the Virasoro algebras. And the quantum version is that this is classical version, and quantum version acting on the operators and the Hilbert space is extended by central terms C, which captures the degrees of freedom and is called the central charge of the theories. So this for right movers and left movers, again, they have a different, one could have different central charges. And again, similar to quantization of the scalar field, one can define in quantum fields a generic vacuum, which is annihilated by this racing operator of Virasoro algebras. And then that generates, in general, some operator on the this conformal transformation and transform in this way. I didn't emphasize that the metric transform as a scale, and similarly scalar field transform with this weight, and these are called the conformal weights. And we can generate a quantum state by applying operator on vacuum using operator state correspondence, and then primary operators, special kind of operators are such that it is annihilated when we use lowering operators. And then we can get the descendant of the given primary operator by applying raising operators, which is, and then you can generate a descending operator. So using this kind of tools, one can explore what's the possible theories. Usually quantum physics, we start with Lagrangian, but here you are enforcing the Virasoro algebra on the state, and you are see the what's the possible. And especially if you look at the central charge between 0 and 1, and also if you insist the number of primary field is finite, then from operator algebra, one has to have some null state in the descendant, and that enforces the number of theory to be discrete series, which is called the minimal models. And the central charge is given in this series, and especially there's a trivial theory 0, and there's an Ising model with central charge 1F, and the 4-5 is a 3-state palm model, and so on. So this is discrete theory of theories, and number of possible primary operators are given here. Now, one thing interesting is character of the theory, which is we define by trace over a single primary with its descendant, then we can generate the weight partition function on given state, and that's called the character. And especially for given conformal weight H, first coefficient is Q to this given by this with a non-trivial A0, and for vacuum character A0 should be 1. And then torus partition function, which is invariant on the, because you are now have a quantum field theory, you can define the theory on torus using some path integral on torus, and then theory should be invariant on the diffeomorphism or general coordinate transformation, especially on the SL2G on Q coordinate. Right, so torus, we have that. Here's the partition function, and then this SL2G on torus is generated by translation and S transformations, and modular invariant partition functions should arise. Simplest, for example, rational conformal field theory with finite number of primary field, which is an extended version of the philosophy algebra, is given in terms of Lie group level K basis general model, which has a Chern-Simons level given in this formulas. Right. So Ising model, for example, has three primary states: vacuum, spin 1/2, and conformal weight 1/2 and 1/16. And they corresponding to really spin is 1/16, and this is related to energy of the Ising models. It's kind of part of that. And then character is given beautifully in theta function and eta functions. And series is given in this form. And this is called the vector valued modular forms, and they transform non-trivially on the SL2G, but such a way that this partition function itself is invariant on the SL2G. And the E8 case turns out that there is a unimodular even self-real lattice in AT, which is E8 lattice. Then one can define theta function, and then one can calculate the partition function of the E8 level 1 conformal field theory with central charge 1,8, which is dimension of the space. And the vacuum character, there is only one vacuum character. There is no other primary field, and it's given in zeta to the 1/3. And it's given in this form. Again, you can see this is the perturbative part, this is the winding mode part of it. And when you expand it, there is 248, which is the dimension of the E8 symmetry. And this linear in Q is captures the current related to these symmetries. And this Q case, again, as I said, the energy momentum tensor is part of it. And this number can split into one, which is energy momentum tensor, then representation of E8s. Right, so one can divide the E8 conformal field theory into smaller pieces. For example, E8 is made of SO16, algebra with spinors. So SO16 is made of, say, SO1 plus SO15 and so on. And SO1 conformal field theory is Ising models, and the SO15. So we know that characters of this, when n is odd, there are only three primary states for this vacuum, this spin SON vector representation, this trivial representation, and this spinor representation. Then three characters. Using that, we can see the E8 character can be written in this form. So that shows very nicely how E8 gets split into two subsets of two commuting or pairs. Now let's go to splitting the monsters. So baby monster, as I said, monster group is huge group, and then baby monster is right below it. And if you look at the monsteralizer dual, then there is 2A is related to if you take away smaller bit of 2A, then you get a baby monster. And that was done by Gerald Huan, 2007. And the way you get is, there's many ways of getting it. One is modular linear differential equation is a kind of tool one can use, and one can find the three characters corresponding to baby monster CFTs. And then one can see this monster partition function, capital J tau, is product of Ising model character times the baby monster character. So vacuum times vacuum, and then Ising model is a primary operators weight 1/2, and baby monster is 3/2, so together it's weight 2. And Ising is 1/16, and baby monster is 31/32, together again 31/16, so together again 2. So naturally, there's a very natural way of splitting this partition function of a monster group into two pieces. So that's what we are trying to generalize. So Fisher group is done again by Huen, Nam, and Yamaguchi. So three-state Palm model of minimal series, and then Fisher group partition function, you can get it again using modular linear differential equation. This character satisfy, and then one can show explicitly that this deconstruction works. So Mackay's extended E8 again is part of this, and what we have shown is this is what, so Kone group comes very naturally as a monster. You lift the Kone to big monster by twisting. So these three things are done, but what we have done is the remaining one, this type of series. So there are, again, a lot of things to remain. We don't know what about this kind of series, but we know conformal field theory corresponding to this rest of the series. So we find all the conformal field theory corresponding to extended E8 thinking diagram suggested by Mackay. So our goal is finding quantum field theory for this BF, this special sporadic groups. And because monsterization pair is given there, and we want to find the corresponding CFT for the smaller bit of the symmetries, then from there we test many ways and then find the theory. But the first thing we have to know is the central charge for smaller bit of theories. And fortunately, this gentleman found the central charge for each bit of theories. So if we subtract from 24 of these smaller bits, then that will be the central charge of the these sporadic groups. And we use many mathematical tools, Rademacher sums, Hecke transformations, or Hecke operators, modular linear differential equations satisfied by these vector valued modular forms, and lattice zeta functions. And then if we know the conformal field theory for small bit theories, then we know the conformal theory for big theories through these relations. Total central charge should be 24, and the product of the conformal weight has to be either 0 or sum has to be either 0 or 2. And using that, and then we have to check if we, after we get the characters, whether this relation is satisfied. So here's the all the Mackay list and the tools we have used, and we confirm all the splitting of the conformal field theory into smaller bit and bigger bit. And bigger bit is conformal field theory for some of the sporadic groups, and also other groups related to extended E8 thinking diagrams. So that's what we found, and we confirmed it. And so let me conclude. So there are more theories in happy family. Remember, 26 sporadic group is split into 20 plus 6 paria groups. So we covered some bit on the top, but the rest of the happy family hasn't been covered. And we have few results on the rest of it, but we are still too busy working on the many other stuffs. So we have some progress on these directions, finding representation or VOA where this sporadic group acts on it. And then there is also supersymmetry one can do on Beauty and Beast. This is called the C=24 CFT with supersymmetry, and whose symmetry is Kone group instead of monster groups. And there is, again, very interesting way of splitting this here into smaller bits. And then, so this I said about it. And then there are paria groups, and there are 6 paria groups, and the people have no idea what kind of, and people have some VOAs, but that's not conformal field theory we are looking for, and we have no idea about what this theory, how we can discover conformal field theory for this series. And C=12, there is N=1 superconformal field theory, which is related to complexified Leach groups, and there's a chain of the Suzuki group, and then deconstruction to Janko groups and so on. And there's a original work by Johnson Frey, the mathematician, in 2019. And we have some work recently done using Fermionic modular linear differential equations. And D=32, which is beyond the string theory, which is critical dimension is 26. So 32 will be too much. But even modular lattice, there are, I heard from mathematicians, 1 trillion of them. So I assume there are 1 trillion conformal field theories, but I have no idea what those theories are. And finally, So there is a related topic, conformal conformal field theory and the Fermionic modular linear differential equations on which we have worked on. And also there is a modular tensor categories and 3D topological quantum field theory, which appears in condensed matter physics and also in mathematics. And they are very naturally related to this conformal field theory because they can appear as a boundary theory of these 3D theories. And also these topics are related to knot invariance and anyons and quantum computers, and also quantum gravity. For example, the capital J tau, this series, Ed Witten argued in 2007, it counts the entropy of black holes in AD3 space. So still, there are a lot of interesting topics related to monster groups so one can wonder about. Thank you.
Thank you very much, Gina.
Hi, hello? Sorry, I can't. Oh, hi. Sorry, can you hear? I can't hear you very well. Sorry. Hello?
Please ask your question. We hear you.
Oh, okay. Sorry. Hi, Kimyeong. Thank you very much for that beautiful talk.
So sorry,
I was coming in a bit late. Thank you. I just have a question. In Mackay's E8 monster observation, one of the key pieces that's missing is the concept of adjacency. So the subgroups are labeled, but the links in the E8 diagram is not clear why they're the links according to the E8 diagram. Does your conformal field theory provide adjacency information?
Yes, so we have something a bit about E8 diagrams. So, right, so E8 is just there, right? So there's no obvious why E8 plays any role there. Right, so.
Yeah, right, yeah.
Right, so here, when we looking for the theory, the smaller bits, we want to regard this with part of the E8 bit of the E8 conformal field theory. C equal to, so you can see the dimension of this central charge is much smaller than 8. So they could be, you can take it instead of from monster, you can take it away from the E8, right? So right. C equal to 8, that hasn't been done except Ising method. I told you that if I have SO15, and then I can take away Ising model, then I get a SO15 from E8. So if I take it away from monster, then I get a baby monster. So I assume there's that sort of story. So if I take it from E8, what's the remaining theory? Obviously, this different type of the theory will be written. And maybe that's the connection for E8.
That'd be interesting. Yeah, that would be great. So I mean, in the sense that, your 1/2 and 6/5, there is a reason that if I remove the 1/2, then it should be the 6/5 next to it.
Right. So 1/2, if I subtract it, then 7/2 will be the theory for SO15. And if we take it this way, I don't know what the theory is, and so on. So that's very natural. I don't think anybody studied that.
That would be very, very interesting, because one of the things that Mackay asked me was the labels 3C, 6A, 4B, 2B, etc.
Right.
According to the monster, but there's no reason why there should be a link between 6A and 4B, for example. Right. They're just subgroup, the subgroups. But in your story, you seem to have some kind of a concept of adjacency, which will be really, really interesting.
Right. In our paper also, there is a story about E7 and E6. The baby monster has E7 and the fisher has E6 and so on. So we have that story also. So there, we haven't figured out all the theories. Some of the spots are empty. So that is again challenging, and maybe using this kind of idea that's subtract from E7, say, conformal field theory, smaller bits, then figuring out smaller bits, then capture the bigger ones, that may work.
Okay. Great, that would be great. Thank you.
All right. Yeah. Right. So Hecke, Hecke is a very subtle math concept, but as a physicist, I know very cheap way of getting the Hecke. So you have a given conformal field theory, then you are imagining wrapping that theory on a circle twice. Then that will be Hecke 2, 3 times Hecke 3. So that's how you get the partition function of free string wrapping n times on a circle. So that's the Hecke. But the conformal field theory is more complicated. It's not free theory. And then when you wrap it, the number of wrapping has to be co-prime to the, there's something called conductor of the theory, which is related to order of the translation as a vector valued modular form. So t to the n with on modular form characters is one only when n with smallest n, that's I think roughly conductor. So you have to think about that sort of things. All right, thank you very much.